Keeper 1.1, Derivative Rules Review. Alright, so here's a list of your basic derivative rules. You guys should remember those from last semester. But remember, we have our sum rule, so we can add derivatives. We can take derivatives of a constant multiplied by a function. Remember that your derivative of a constant is 0. And then also remember that the derivative of your linear term is just the coefficient. Alright, so our first rule that you should remember from derivatives is the power rule. So if you remember with your power rule, you take your exponent, drop it to the front, and then subtract 1 from your new exponent. So if we were looking at the derivative of x to the n, it would be n times x to the n minus 1. The derivative of e to the x, if you remember, is just e to the x. And then if you had something being multiplied, like the derivative of f of x times g of x, remember you do first times the derivative of the second, plus second times the derivative of the first. For our quotient rule, so if we have two things being divided, you're going to do low d high minus high d low over low low. And then you have your trig derivative. So the derivative of sine is cosine, derivative of cosine is negative sine, derivative of tan is secant squared, derivative of cosecant is negative cosecant cotan, derivative of secant is secant tan, and then derivative of cotan is negative cosecant squared x. Alright, so next we have our chain rule. So if you remember chain rule, you want to take the derivative of your outside function and work all the way into your inside. So your outside function in this case would be the derivative of f of x, with g of x staying the same. And then you want to take the derivative of g of x. Alright, so if you have a function in the form of a to the x, to take that derivative, remember you rewrite the exponential a to the x, and then you do ln of whatever that a is, whatever the base is. Your derivative of your natural log is 1 over x, and then your derivative of your log base a of x would be 1 over x ln a. Alright, so here's our first example. It says consider the function x squared plus xy minus y squared equals 5. They say calculate dy dx. Alright, so remember we have to kind of do this implicitly because we have xy on the same side. So I'm going to start with my original function, and then I'm going to take the derivative of each piece. So the derivative of x squared is 2x. And then that middle piece, xy, remember we have to do product rule. So I have first times the derivative of second, which is x dy dx, plus second times the derivative of the first, which would be y times 1. And then it should be minus 2y dy dx. The key to it is just remember every single time you see that y, that you write that dy dx afterwards. Alright, so now simplifying, I move everything to the other side that doesn't have a dy dx. And then I'm going to factor out the dy dx on the left side. So I have x minus 2y times dy dx equals negative 2x minus y. Lastly, I'm going to divide by the x minus 2y to get dy dx by itself. And there I have my derivative. So dy dx equals negative 2x minus y all over x minus 2y. If you want to clean it up a little bit more, you can by factoring out a negative or really multiplying everything by a negative 1. And so you'd have dy dx equals 2x plus y over 2y minus x. Alright, so example 1 continued. We have the same function, and they want us to write the equation of the line tangent to C at the point 3, negative 1. So in order to figure out the equation of the line tangent, we must first take our derivative and find the derivative at that point. So from part A, we have that the derivative is 2x plus y over 2y minus x. And so what I'm going to do is I'm going to plug in the point 3, negative 1 into that derivative and simplify to get that my derivative at 3 is negative 1. Alright, so now plugging that into my equation of the line formula, I get y plus 1 equals negative 1 x minus 3. I can actually leave my answer like that if I want to, or I can clean it up to make it a little bit nicer by distributing the negative 1 and subtracting the 1 over to get y equals negative x plus 2. Alright, so example 2, they're asking us to find the third derivative of the function at x equals 4, given that the function is y equals 2 over square root of x. So the first thing that I'll do is I'll rewrite the function as y equals 2x to the negative 1/2. And then I'll take the first derivative by doing the power rule. So when I do that, I get negative 1 x to the negative 3 over 2. Then I'm going to take the derivative of that using the power rule to get 3 halves x to the negative 5 halves. And then doing it one more time to get the third derivative, I'm going to have negative 15 over 4x to the negative 7 halves. Now evaluating that at x equals 4, I plug 4 into my function. I get negative 15 over 4 times 4 to the negative 7 halves, which reduces to, or which cleans up to negative 15 over 4 times 128, which equals negative 15 over 512. Next, we want to find the derivative of the function z equals e to the y over y squared. So understand that we're really taking the derivative in terms of y here. And so I'm going to use quotient rule. So we have low d high, or y squared times e to the y, minus high d low, e to the y times 2y, all over low low, which would be y squared squared. Once I clean that up, I'm going to have y e to the y minus 2 e to the y over y cubed. And then, again, I can clean that up a little bit more by factoring out the e to the y. So I'd have e to the y times y minus 2 over y cubed. All right, so the next example, they're asking us to find the derivative of h of r equals r squared minus 2r times e to the r. We have two things being multiplied here, so that means we have to do the product rule. So I'm going to do first times the derivative of the second plus second times the derivative of the first. All right, once I have that written out, you can either factor out the e to the r here, or you can distribute in your e to the r. Just for simplicity, I'm going to go ahead and distribute mine in. And so I distribute the e to the r to every single term. And then I'll add like terms to get r squared e to the r minus 2 e to the r. You can leave your answer like that, or you can go ahead and factor the e to the r back out to get e to the r times r squared minus 2. The next example, we want to find the derivative of tan inverse of 1 minus x. Remember, your rule for tan inverse is 1 over 1 plus x squared, or whatever the argument of the tan inverse is. So I'm going to have 1 over 1 plus 1 minus x squared. And then we have to chain rule that, so we have to take the derivative of the 1 minus x, which is negative 1. And then cleaning that up, I'm left with 1 over, or negative 1 over 1 plus 1 minus 2x plus x squared. And then adding like terms, I get negative 1 over x squared minus 2x plus 2. All right, so our last example, we have the function y equals x to the ln x, and they're asking us to differentiate. Because we have the x in the exponent, we're going to have to do like a logarithmic type differentiation on it. So we're going to take the ln of both sides. And so I'm going to have the ln of y equals the ln of x to the ln of x. I'm going to drop that down using my log rule. So drop the ln of x down. I'm left with ln of y equals ln x times ln x, which is really just ln x squared. So now I can take the derivative of each side. I'm left with 1 over y dy dx equals, and on the right side, I'm going to chain rule it. So 2 ln x times the derivative of ln x, which is 1 over x. And then I'll multiply both sides by y to get the dy dx by itself. So I have dy dx equals 2 ln x over x times y. And then my last step before I simplify, will be to plug in that y. So the original y was x to the ln x. So my dy dx is now 2 ln x over x times x ln x. And then I can clean that up a little bit more if I want to get rid of the x in the denominator. I could just bring it back up. So I have 2 ln x times x ln x minus 1.